So as people rejoin, um, if you got through, could you put in the chat, either to me or to everyone, what fraction of the sun's hydrogen we thought was going to get burned? So the answer to question 6, if you got there. Cool. So it looks like people got 0.03, so about 3% of the sun's hydrogen. Okay, we should all be back together. So yeah, around 0.03 or 3% of the sun's hydrogen is actually going to be converted into energy with what we think of how long the sun is going to live. And people were thinking, like one group I talked to was like, that seems really small. And it is pretty small, but what we have to remember is that for this estimation we just did, we made some pretty big assumptions. First, we assumed all of the sun is hydrogen, which it's not. Not all of the sun is hydrogen. So that's something we have to take into account. Only about 70% of the sun by mass is hydrogen. So there's fewer hydrogen atoms than we just predicted. Second, only the hydrogen that's in the core is ever going to get fused into helium. So only, I said 40% of the sun's mass is going to even have a chance of being converted into helium. So that's another big part that's going to change how long the sun can actually live, how long the sun can continue fusing hydrogen to helium. So those two things together, also there's just some physics. As we convert hydrogen to helium, there's less hydrogen in the core, which makes it more difficult to slam 4 hydrogen atoms together, even if there's still enough to burn. So there's also a little physics that goes into that calculation. But you guys just estimated how long the sun will live, which is pretty cool. We do know where the sun has burned for about 4 billion years, and so we think it'll burn for about 5 billion more. So nothing to worry about with the sun going off. It's got plenty of fuel to continue generating light to sustain us for a while. So I just want to go a little bit into how we know that this is what's happening. I have said this many times, but we cannot see inside the sun. So we need to use other methods to figure out what's happening in the sun, and that then there are ways that we can be pretty darn sure that the sun is fusing hydrogen into helium to create energy. So the models we use we use measurements of the radiation from the sun, and a bit of physics to kind of work through and figure out what's happening. So the first thing we can kind of think about is pretty much what you guys just did, but we can look at how much energy the sun produces and try to think of different ways we could produce that much energy. So in this activity, you saw the sun outputs about 3.85 times 10 to the 26 watts constantly. So watts are joules per second. So that's a unit of time. And remember, we can compare that to a light bulb. Light bulbs are typically about 10 to a couple hundred watts. So the sun is 3.85 followed by 26 zeros. So much brighter, much more energy than a light bulb. About 10 to the 24 light bulbs of the sun. It's also about the same amount of energy if we were to take all of the nuclear weapons on Earth and explode them all at the same time. You would multiply that by 4 million to get the energy of the sun. So the sun is outputting a lot of energy pretty constantly, period, sorry. So since we know how much energy the sun is outputting, we can try to think about how we can produce energy on Earth and compare those to that amount to see if the sun were doing other things, how long could it live? So for example, you could ask, okay, the sun kind of looks like a fire. Is it possible the sun is just a big fire out in space? But that's not possible. We can't produce the amount of energy we see from the sun with just a fire. So when we burn 1 kilogram of coal, that produces about 29.3 times 10 to the 6 joules of energy. If we then did what you guys just did and kind of divided the sun's luminosity by that 2.93 times 10 to the 6th, and looked at how massive the sun is, which we can find using Kepler's laws, we can see that with combustion, if the sun was just a giant mass of burning coal, the sun could only shine for about 4,800 years. The sun's been shining for a lot longer than that, so there's no way that the sun is just fueled by combustion. We could also consider if the sun could be fueled by gravitational energy. So both Jupiter and Saturn, when we talked about them, we noticed that they were collapsing just slightly, and as they collapsed, they were radiating energy away. So the sun could do this as well. There's some complicated math and physics that go into this, but what people have found that is if the sun was collapsing and it continued to collapse until it was a black hole, the sun could shine, radiate gravitational energy for about 100 million years. But if that were the case, we would see the sun shrinking about 20 meters every year, which we don't. Also, the sun has been burning for more than 100 million years, so gravity has to be out, which leaves fusion. And as you guys saw, you just did the math to show that through fusion, the sun can actually sustain the energy it outputs over time. So fusion is good. And that also tells us that the sun's core must be at least hot enough to fuse hydrogen into helium, because that's what the sun is made of, which we know because of the spectra. So using these kind of models of what the sun could be doing to create energy, we can kind of rule things out until we find what it must be doing. So that's how we know that the sun is fusing energy, and that's also how we know the temperature of the core. Another thing that gives us some hints about what's happening inside of the sun is the fact that the sun is not expanding or contracting. The sun is a big mass of plasma, which is kind of like a gas, you know, that charged gas we talked about on Tuesday. So if there was nothing pushing it out, gravity would pull it all in and it would collapse again until we formed a black hole. So there must be a force opposing gravity to keep it at the size that it is. And that's the radiation pressure from photons being produced inside the sun. So as energy pushes out, gravity pulls in, and the sun remains in something called hydrostatic equilibrium, which just means it's not changing size. It's a constant sphere of one solar radius. Sorry, I should have looked that up, but it's not changing size over time. So the pressure from the nuclear forces inside the sun must be equal to the gravity holding it in. And that tells us a bit about the density and temperature conditions in the sun as well. Another thing we can measure from the sun to learn a bit about what's happening inside is solar neutrinos. So all of those reactions, all those fusing hydrogen to helium reactions produce neutrinos as well as energy, sorry. Neutrinos are very, 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 very small neutral particles that can escape the sun more quickly than photons. So because they don't carry charge, because they're neutral, they can move through all that junk inside the sun without bumping into it, and they can travel to us much faster than the photons that are created in the sun. A kind of cool little fact, if you drew a 1 centimeter square on your hand, there are about 100 billion neutrinos from the sun passing through that centimeter square every second. So neutrinos are streaming through us all the time, but because they are neutral, they do not harm us at all. They just pass right through and continue on their way. We can detect solar neutrinos using special detectors like the Super Kamiokande, which is what I've shown, whichever direction it is for you, which is a big detector of neutrinos, a big vat of water that is looking for Cherenkov radiation from the neutrinos bumping into the water molecules. So Cherenkov radiation, if you've ever been to a nuclear reactor, you might have seen it kind of glowing blue light, and that's Cherenkov radiation. Cherenkov radiation is kind of similar to like a sonic boom, but in light. So when you when something moves faster than the speed of sound, you get a sonic boom. If a electron can move faster than the local speed of light, not the speed of light in a vacuum, nothing moves faster than that, but certain materials will actually slow down the speed of light, and you can accelerate particles over that speed of light. When they do that, they produce Cherenkov radiation, which is this funky blue color. The neutrinos neutrinos will occasionally bump into electrons and accelerate them to faster than that local speed of light, so the speed of light in that material, and that produces this Cherenkov radiation. So we can use that to measure the flux, the amount of solar neutrinos coming from the sun. And that also tells us that there must be fusion happening in the sun, because that's how we would generate this amount of neutrinos that we see. The last thing that I'll mention really quickly is that, I think I said this just very briefly earlier as well, we can use sunquakes to study the inside of the sun. Just like we used earthquakes to measure the interior of the Earth, we can use ripples on the surface of the sun to measure what's happening inside of the sun. So there aren't obviously tectonic plates on the sun. There are no continents. The whole sun is just a big ball of plasma. So quakes are different, but pressure changes, pressure variations, temperature variations along inside the sun and along the surface can create kind of waves on the solar surface, which are similar to earthquakes. And we can use measurements of how those waves travel to figure out what's happening inside of the sun. So we can't go inside the sun, but based on the amount of light the sun is radiating, we can figure out how the sun must be generating energy. Based on the solar neutrinos, we can think about what fusion processes are happening, how many of them are happening. Based on the quakes on the surface of the sun, we can get some idea of the pressure and temperature conditions. And also knowing that it's fusion tells us a bit about what the conditions inside of the core must be like. So that's a bit about the interior of the sun and how we know that. Does anyone have any questions before we start talking about other stars? Okay, so let's jump over here. So this is astronomy is, the study of stars. So we're about halfway through the semester and we're finally talking about stars outside of our own solar system. But the reason for that is all these stars are really far away, so it's hard to get measurements of them. And we really need to compare them to what we see in our own sun to learn a lot about these stars. So just to compare to the sun a little bit, the sun is the only star close enough that we can resolve the surface. So what I mean by that is, like, if you think of trying to take a picture of your friend across Ankeny, in the picture, their face is gonna look blurry because they're so far away that you can't resolve the details of their face. All stars are really, really far away. So when we take pictures of them, we're seeing them as a point and we can't really get any details on their surfaces. So we can't do that same helioseismology. We can't necessarily it's harder to see the exact size and the conditions of the surface, but we can get a lot of information just by looking at the light that these stars radiate. We can still learn a lot about them. Just as a quick example, I wanted to think about, where the nearest star would be on our scale model. So if you did the scale model lab, I know most people made their own scales, but the one I suggested was that 10 meters is 1 AU. So 10 meters is the distance from the Earth to the sun would be 10 meters in this model. So if we were to use that model, we can also think where the nearest star would be. So the way we find that with scale models is we take the distance we're interested in. So right now the distance we're interested in is this 4 times 10 to the 13, which is the distance between the sun and the nearest star, Proxima Centauri. So we're going to take that value. Sorry, my writing's a bit ugly. It's hard on the screen. And we're going to multiply it by our our scale factor, which is going to be 10 meters is equal to, so 10 meters divided by the distance between the Earth and the sun, which is 1.49 meters. There, 49 times 10 to the 8 kilometers, sorry. misspoke there, did not finish my thought. So if you multiply this through, you should get that on our scale model, Proxima Centauri would be about 2.68 times 10 to the 6 kilometers away, which is equal to about 1.66 million miles, or approximately 66.8 times the circumference of the Earth. So you would have to go around the Earth almost 67 times to get to the nearest star if we are in our scale model where the Earth is 10 meters away from the sun. So the main reason I'm telling you this is just to point out that the nearest stars are very, 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 very far away. We cannot travel to them. Light takes about 4.3 years to travel between us and Proxima Centauri, and that is the nearest star. Most stars are further than that. Let's continue. Because of that, it's very, very difficult to measure surface features on other stars like we could with the sun. And just again, to kind of point this out in one more way, the biggest star in our sky is Betelgeuse. So that's the head of Orion here. Right now, I have noticed Orion is up in the very early morning. So if you go outside while it's still dark, which is lasting longer and longer now, you can see Orion kind of near the horizon. Often people can notice it because they can see these 3 stars that form Orion's belt, and they can measure those. Betelgeuse is Orion's head. It's the biggest star in our sky, but it's only 50 milliarcseconds, which is very, very small. So there's 60 arc seconds in an arc minute, 60 arc minutes in 1 degree. The sun is about half a degree, or 1.8 times 10 to the 6 milliarcseconds. So the sun is, almost 10 to the 5, about 10 to the 5 times bigger than Betelgeuse in the sky. So much, much, much bigger in angular size. Despite the fact that we can't see their surface, we can still measure their spectra. And from their spectra, we can measure their temperature by looking at the peak of the spectra using Wien's law. And we can measure their composition by looking for dips in the spectra to figure out what atoms must be present on the surface of these stars at least. We're going to talk about these in the next few weeks. We can use some tricks to find their mass, their radius, their age, as well as the distance to these stars. So right now, based on what we know so far, we can get their temperature, their composition, and then with a few other tricks, we'll be able to find their radius, their age, and their mass, and the distance to them. So the first thing we're going to think about is how we could find distance. If we remember back to when we first talked about light, one of the things we learned is that light falls off as the square of the distance. So that was that inverse square law. The further something away is, the dimmer it will be. The problem is, in order to use the inverse square law to find out how far away a star is, we need to know how bright the star is. So there's kind of 2 things going on here. Stars are different brightnesses. Not all stars are the same brightness. So stars will look dimmer both because they are farther away and just because they are dimmer. So dim stars look dim, whether or not they are far away. Bright stars look bright, whether or not they are far away. So we need to know the star's intrinsic brightness, how bright it actually is, in order to use the inverse square law to define the distance. But if we do have a method of finding the star's intrinsic brightness, then we can use the inverse square law to find a distance. One way we can do this is we can look at the color of a star. So the color of a star is going to give us some hints about the actual brightness of the star, which we'll talk more about as we get into different types of stars, which probably is going to be next class, but still. So I wanted to just pull up, if you think about, we can use in astronomy, we use filters. We can put filters on our telescope that are going to look kind of like these slides here that I'm holding up, sorry. And when we put those on, those block certain colors of light. So when you look through this filter, I look really yellow because only the yellow light from me is coming through zoom and reaching you. Or on this filter, it's hard to see. Let's try a different one. How about maybe this filter is, here we go. The red one looks better. Sorry, this filter is pink, a red filter, so only the red light from me is getting through to you when you look through this filter. So we can look at this to find the color of a star by seeing how bright the star is when we look through a red filter and how bright the star is when we look through a blue filter, and comparing those to figure out which color the star is brightest in, which gives us an idea of its color. If we know its color, that'll also give us some indication of how bright the star actually is, just period. And that's because color and temperature are related, and hotter stars are going to be brighter. So the hotter a star is, the brighter it's going to be, and color is going to be really closely related to temperature. And that's because of Wien's law. So just wanted to show, sorry. My Zoom things are getting in the way. So if we have a black body through Wien's law, so stars are going to be pretty close to these black bodies. Radiating light is a function of color. So again, this is how bright a star would be as a function of color. And I've also shown here some filters. So UV filter would only be looking at light in these wavelengths. So you'd measure how bright the star was at these wavelengths. These UV wavelengths. A blue filter would only be looking here. We can see as we change the temperature of a star, that peak changes. And depending on where that peak is, so here we would see for a cooler star, we would expect to see more blue and green light and less UV light. For a really cold star, we would start to expect to see more red light and almost no UV light. And for a really hot star, when I turn the temperature up to, over 10,000, we would expect a lot of UV light and not very much red light. So by looking at the color, we can get the temperature, and we can use that to find the brightness as well. So a little thing that I wanted to touch on here as well, so we're almost done, I promise, is that most stars are going to be, on average, most stars are going to be less luminous and smaller than our sun. So we think of our sun as kind of a medium-sized star, but most stars are going to be small stars, and we're going to have a few really, really big stars that are much, much larger than the sun. But we're not going to get many really, really bright stars, but we're going to get a lot of really, really small stars. Really bright, really big stars, we're going to have a lot of really small stars. And the way I like to think about this is if you think about breaking a plate, when you break a plate, if you drop one on accident, you're going to end up with a few really big pieces and a lot of really, really small pieces that you find when you walk across this floor and you aren't wearing socks and you cut yourself because they're hard to sweep up. And so the same thing happens when stars form. Stars form out of giant clouds of gas. As these clouds of gas get dense enough, they start to collapse and merge, clump together to form stars out of these things of gas. And from that cloud of gas, you'll get a few very big stars, a medium amount of medium stars, and a ton of really small stars. So in our sky, most of the stars we see are the really, really bright stars, but that's not most of the stars that are near us. Most of the stars that are near us are actually the really small, faint stars, but they are so faint that even though they're close to us, we can't actually see them. Another thing we can do to get an idea of how bright a star is we can look at its spectra. So this is a spectra of a star. If you've done the Sun Lab, you'll have seen the spectra of the sun. And what we can learn from this is we can look at the peak of the spectra to get a temperature. So again, this is taking the light and it's looking at it as a function of wavelength. So how bright is the star as a function of wavelength. So a function of color, where we have red over here and blue, or sorry, blue over here and red over here. We're taking like through a prism and seeing how bright the star is as a function of color. Based on where that peak is, we can get a temperature, and based on where the dips are, we can find the composition. So we can use that as well to classify stars and figure out how bright they actually are, which we can then use to get distances to these stars. So that's what we're going to do next class, is we're going to make our own classification system for stars. But before, in the last few minutes, I just wanted to quickly point out that we are here-ish. I'm slightly behind, but I think we're going to catch up eventually when I take out this activity and kind of move things around here. So that means we've done about 2 weeks of our Stellar Scientist badge, which means we have about 2 weeks left. So this is a good time to start thinking about earning those lab points, earning those homework points. You have quite a few ways to do it still. So if you go to your assignments, a few people have been turning in their biography, citizen science project, open-ended project, and article podcast projects. So those are options. The Stellar Science homework is available still, and some of those are, you could start looking at that even if you didn't quite want to finish it yet, but that's an option. And then there's also still 4 labs open that we have covered most of the material on. We haven't quite gotten to these last 2, but the Sun Lab is one that a few people have done. Inverse square law, where you can do that inside. And if you do get outside this weekend, if it's not too rainy, the Parallax Lab and the Measuring Spectra Lab would be nice ones to check out. Just remember, to do the Measuring Spectra Lab, you need to get your lab equipment. And if you are in town, you have to pick that up from the Reed Mailing Center. If you are out of town, it should be on your way to you, if not in your possession already, in the letter from me. If you have not gotten it and you are out of town, it might mean I did not get your mailing address. So that might be another reason why you have not gotten it yet. And of course, there are also reading quizzes that you can do to get homework points. Just a reminder, if I have been having some issues with images, but I am hoping that they